Okay, this is Intro to Stresses in Beams number 2. Well, first we have to figure out the reaction load, so I'm going to isolate the whole beam. We have a force this direction of 6,000 newtons, a meter to the right of there. We have a force of 8,000 newtons, another meter to the right. We have this unknown reaction. Since all the external forces are just horizontal, this reaction is only going to be horizontal. And then over here, we have a force of 10,000. At that pin joint where I have the R, you also, a pin joint normally is a full unknown vector of forces. You could do that and you would just see that the Y component was 0. So I'm just this is sort of a shortcut. Okay, so we have to figure out what that R is. Newton's second law, I'm just going to use the X component of that equation. And it says negative 6,000 minus 8,000 plus R plus 10,000 is equal to 0. And so that is, let's see, R is equal to 4,000 newtons. Okay, so now we can do the cuts, and the cuts for this are going to happen, well, the cutoffs between the cuts, the places where the subfunctions of these internal loads is going to change, are where this 8,000 is and where this R is. So I'm going to do the first cut that's going to represent X values between 0 and 1 meter. And I'm going to do that. So I'm isolating a piece that goes all the way from the left to not all the way to the 8,000 Newton force. Okay, so we do have the 6,000 on the end. We don't have the 8,000 yet, so now we have the internal loads. V and M, you could write them in there and you just calculate that they'd be 0 using the usual calculation. So this one, nothing's going on but horizontal load, so I'm only going to calculate that T. So Newton's second law, X component says negative 6,000 plus T is equal to 0. So the internal load is positive 6,000 newtons. That's for every point in this range of X values from 0 to 1. And now I'll go to cut 2. This is valid for all X values, sorry, not from 0, from 1 to 2. We're still going to do our cut. The piece that we're isolating still goes all the way from the left, so we still have the 6,000. But now we also have the 8,000. And then the internal load. So Newton's second law says negative 6,000 minus 8,000 plus T is equal to 0. So T is equal to 14,000. And then the last cut is for X values from 2 to 3. So now we're including the 6,000. we're including the 8,000. We're including the reaction load, which is 4,000 going the other way. And then we have the internal loads that for every cut here, the only one that's non-zero is T. Newton's second law, X component says negative 6,000 minus 8,000 plus 4,000 plus T is equal to 0. So T is equal to 10,000. Okay, so what this is saying is if you plotted out the internal tension as a function of X, so there's 1 meter, 2 meters, 3 meters, you would have a value of 6,000 over the first part, a value of 14,000 over the second part, and a value of 10,000 over the third part. Most people draw these connected like that, although we don't know what's happening at the boundaries of those subfunctions. Okay, so what we see here is that the internal load is tension over the whole thing, and the tension is the greatest in that middle section where it's 14,000. Now we're going to calculate the stresses, the stress tensors for, all the points in that first meter have the same internal tension. All the points in that second meter have the same internal tension, and same with the third meter. So we really only have to do 3 calculations. So on that first meter on the left, we can use our formula for sigma xx, and that's just going to be T over the cross-sectional area. The cross-sectional area is 0.05 times 0.02. So that's 1 times 10 to the minus third. The tension on that first part was 6,000, so we have 6,000 newtons over 1 times 10 to the third meters squared. And so that's 6 times 10 to the 6 pascals. This is not third, this is minus third. So 6 times 10 to the 6. And so the stress tensor has that as the X element, the X normal stress. Everything else is 0. And now we go to that middle meter. For that one, the X normal stress is, so we have 14,000 newtons divided by the same cross-sectional area. So that's, all right, it is 14 times 10 to the 6 pascals. And so the stress tensor looks the same, except that we just have that value in the X element. These are all positive because the member is in tension over the whole length. And then on that 1 meter length on the right side. Our stress is 10,000 newtons. And so we get a value of 10 times 10 to the 6th pascals. I'm just keeping the times 10 to the n part the same so you don't get confused, jumping around. So you can see the ratios between those. And we have a stress tensor that's equal to 10 times 10 to the 6, 0, 0, zeros everywhere else. Okay. And now, so that was part A. Now for part B, we want to calculate the strain. And to calculate the strain, the Voigt strain is equal to the compliance matrix times the Voigt stress. For the compliance matrix, you need to know the Young's modulus and the Poisson's ratio, and you can just Google those. But a good one for aluminum is a Young's modulus of 69 times 10 to the 9th pascals. Poisson's ratio 0.3. And so CMPL and now we're going to multiply that by the stress tensor. I'm going to choose just one of these three, but the idea is to do it for all three. But I'm going to do it for, like, as my example, I'm going to do on that middle meter. And why would I choose that one to do? Well, that's the one where the stress is the highest. So if the part that we're most concerned about is the part where you have the highest stress. And so this, if you're only going to do one of these three, this is a good one to do, but you should do all three just to get the practice. Okay, so for that one, our Voigt stress has a value of 14 times 10 to the 6th, and zeros for all the other values. And what you get is 2.03 times 10 to the minus 4th. Negative 0.61 times 10 to the minus 4th. Negative 0.61 times 10 to the minus 4th. 0, 0, 0. Okay, so what we saw is that for that middle member, not the middle member, for that middle meter of the beam that we're looking at, we have an elongation along in the x direction. That makes sense because it's in tension. And then in the y and z direction, we have contraction that comes from the Poisson's effect. If you stretch in one direction, you get contraction in the other two perpendicular directions. Okay, so now what about steel? Well, it's the same exact thing, except so we're still going to use the same we're still going to, everything's going to be the same. We're still going to calculate it as the compliance matrix times the Voigt stress. The only thing that's different is now for steel, our Young's modulus changes to 200 times 10 to the ninth. It's a much stiffer material. So you apply the same force to it, it stretches a lot less. We'll still use a Poisson's ratio, 0.3. And for this one, you get a Voigt strain that is 7 times 10 to the 7 times 10 to the minus 5, negative 2.1 times 10 to the minus 5, negative 2.1 times 10 to the minus 5, 0, 0, 0. Okay, so with steel, we got a much smaller set of strains, although the reasoning is the same, where it stretches and where it contracts. But it's a smaller strain because it's a stiffer material. If you have the same stresses in a stiffer material, you get less deformation. And so that's how that problem works. That was Introduction to Stresses in Beams number 2.